I'd like to get going right away so that we can try to get back on schedule. Our final session this morning is materials designed for aerospace application, and this session will be chaired by Professor Nitin Padture. Nitin joined us here at Brown University from Ohio State in January of 2012, and Nitin was the founding director of the NSF-funded MERSEC program at Ohio State. And he's a world expert in the field of synthesis and processing of materials for a variety of aerospace and electronics applications. Nitin.
Thank you, Larry. So I had some slides to set the discussion, but I'm going to skip that in the interest of time. And just introduce the speakers. Oops.
I realize I'm competing with many growling stomachs here, so I'll try to speed it up. My name is Dave McDowell. I'm at Georgia Tech. And in terms of background, I sort of straddle the fields of computational materials science, computational mechanics, and systems design. So my comments will be of that ilk that sort of combines those perspectives. Oh, there, okay, gotcha. So we've seen in the previous talks some mention of programs such as DARPA Accelerated Insertion of Materials back in the early 2000s. This notion of integrated computational materials engineering that emerged from the National Academy of Engineering NMAB study. And materials by design, which really Greg Olson kicked off with his Steel Research Institute at Northwestern University in the mid-1980s. But they're leading along the same pathway with common themes. They embrace common themes. The demand for improved materials for emerging technologies, decreasing the time to market, increasing the concurrency of materials discovery and development and product design with added functionality. And this strongly couples with manufacturing competitiveness. As we think about bringing manufacturing back to the USA, we should do it with the value added of these kinds of strategies. So it all points to really concurrency of these different phases, fully consistent with what Cyrus talked about with the MGI linear continuum earlier this morning, which I show here. Sort of recap the need to try to drive down the materials discovery development cycle to be more in line with the product design and development cycle. Historically, in the aerospace industry, the development and certification and incorporation of new materials has been on the order of 10 to 20 years, whereas one can now realize next generation aircraft in just a few years, because that's very heavily CAD driven. But I would go a step further and decompose this continuum into two parts. One that we've heard of extensively before with Professor Cedar and Professor Rajan, the discovery phase, which is heavily related to first principles calculations, of interest discovery of stable phases and their properties, and application of informatics and data-driven schemes to identify outliers, classify outliers that may be of interest to pursue for breakthrough performance. ICME, Integrated Computational Materials Engineering, really also has to do with the development and certification and manufacturing phases. So you put them together, you really have the essence of MGI, which is discovery and development. Then we can speak of discovery, development, and selection as three different strands. So the two strands that I've just mentioned, discovery and development, have to do with MGI. But the fact is that the way we teach materials design, quote unquote, in universities and in materials science departments across USA and even in Europe is as a material selection problem, i.e., given a tabulated database, we select using constrained optimization the best solutions, right, after Mike Ashby's approaches with Granta software. But I think most of the opportunities lie in the discovery and development phases. And I just point out here that in development, oftentimes it's metastable phases that we rely on for in-service performance characteristics. You know, that if you take them up another 50 degrees centigrade, you'll get coarsening and you'll destroy the structure. But you go up to that ragged edge and you understand the kinetics of the coarsening behavior, segregation, et cetera, that limits that. And especially in the aircraft gas turbine engine business, this is a big consideration. So if you think of these two complementary strands, discovery and development, you can really go back to the last decade of initiatives and outline them accordingly. Thinking of the NSF, DMR, cyber discovery, DOE, computation materials, science and chemistry, simulation-based engineering science, which could straddle the two back in this is actually 2006. And then the development and upscaling, the DARPA AIM program was a good example of kludging together existing tools and databases and then undertaking, as Dave talked about, an exercise to try in gas turbine engine materials to decrease the weight of the disk while increasing burst speed performance strength. Now, the same thing was done with Boeing and composites within the DARPA AIM program. And ICME is part of this development strand as well. I think the Materials Genome Initiative sort of connects the two strands in that it emphasizes both the discovery of outliers and classification of outliers that we should pursue. And as Professor Cedar talked about, characterizing the universe of stable phases that we have considered or have not considered, right? And of course, the ICME strand of MGI would be the development, certification, incorporation, coupling with systems design. My comments will have more to do with the development strand, given the focus on aerospace materials. Dave talked about this already, so I'll not belabor it, but this is the DARPA AIM program that Leo Christodoulou had headed up back in the early part of the 2000s. I think it started around 2000. And the interesting thing here was it's a partnership of the OEMs, both GE and Pratt were involved. And I think it's safe to say that before this, all the proprietary issues, information sharing and so forth were always, that was always an issue. I think AIM was one of those programs that showed how it could work in a pre-competitive mode to bring together tools that were of common interest while you have your proprietary materials and databases. This is the way of the future to target the pre-competitive tools and methods and develop the sort of combined methodologies that can then be lifted and used by other applications in other industries. So this was exciting in that it combined material modeling, material characterization, all the way to processing. Forging and heat treatment were included in the AIM methodology. But of course, it's not all about modeling and simulation. As Professor Cedar says, we don't design materials just based on computer simulations, right? In fact, when we formed the Center for Computational Materials Design, it's an NSF Industry University Cooperative Research Center, back in 2005, Zeke Liu at Penn State and myself, we did sort of a survey and we estimated that only 10% or less of the decisions, the fraction of the decisions made in developing materials at that time were being informed by modeling and simulation. So we're not talking about a grand vision of 100% decision support or 90%. We're talking about moving that up to 20 or 30%. Those kinds of things, that's the value added in terms of decreasing the time for the development strand of ICME. Some comments on aerospace alloys that I think are relevant to the discussion. It's important in discovery to look for stable phases. It's important in development to understand phase interactions and metastable, non-equilibrium phases, and how you engineer those, understand the kinetics. The thermodynamics is still extremely important. And also, I would say that one weakness in a lot of our strategies for hierarchical computational simulation is in our lack of understanding of the role of interfaces and the interplay of interfaces with defects of various types, point and line defects, and the structure of interfaces and how that changes with time and service. I would also add that processing You know, you take these aero alloys, residual stress is terribly important. Of course, we want them in there in terms of laser shock peening or shot peening to improve fatigue resistance. But they arise also through thermomechanical processing, can be alleviated with heat treatment. Composition gradients, even at the micro scale, porosity, inclusion, segregation, coarsening, these all have a strong effect. And some of them are considered as extrinsic in nature, right? So something like a non-metallic inclusion, you know, you wouldn't necessarily call that an intrinsic microstructure feature. It arises due to the process where you're forming ingots, right? So you have to understand the life cycle of the process, route, and structure and property relations. This, I think, is a useful way of thinking about an early impact of MGI on the way we view classical material science decomposition of process, structure, property, performance relations. This overlapping Venn diagram is from Greg Olson's 1997 paper in Science, where he laid out very nicely the fact that, you know, normally we do bottom-up scientific inquiry of those relations, but the design problem is the inverse problem. You start with desired performance and you work your way back through the properties, structure, and process that's necessary to achieve that. Well, historically, our focus has been on the interface between properties and performance, right? That's the material selection problem. That's the way we teach it. It's a big change of culture to teach it any other way, I can assure you. That's an important directive for MGI. But what we're seeing now is the shift to the taxonomy of interest. The language of relevance here is really the structure of the material. Even for the same composition, because we're interested in non-equilibrium process paths and metastable structures, even the same composition can have vastly different microstructures, and those are essential to conferring the proper desired performance characteristics, right? And so it's extremely important that our taxonomy is at the level of microstructure, including composition. So this is you know, referencing Dave's talk. You know, we talked about materials folks needing to speak the language of design engineers. Well, you know, one could also argue that we need to pull property performance, design type relations back to this level, but practically speaking, it means that we have to map out the probability density functions of the appropriate properties and response characteristics based on our understanding of the available microstructures. So it's no longer a world of deterministics, it's a world of stochasticity, right? We need to speak in terms of this mapping being a probability density function based type of mapping. So in the CCMD, Center for Computational Materials Design, we work mainly in aerospace materials, nickel-based superalloys, titanium alloys, some work on martensitic steels, some work on aluminum and magnesium alloys. But here's the way we frame the design problem, consistent, I think, with the discussions today. You know, something like a Dreamliner, that can be designed on the computer pretty much in a relatively short time frame using geometric tolerancing and finite element analysis and so forth. But these are horribly complex subsystems and then parts that comprise the individual subsystems. But we have a pretty good handle on top-down design. You know, the large OEMs do this rather well. What we don't have a handle on at all is the way of moving this design chain down through microstructure from macro through mesoscopic microstructural levels down to molecular and quantum levels. And one of the big reasons is that we can only do bottom-up calculations. You can't invert these calculations because they're dynamic, they're not all thermodynamic in all cases. And by sequencing combinatorially through a number of stable phases, mapping out phase diagrams, assuming stability, one can actually say a lot in terms of the potential to inform, let's say, Ginsburg-Landau potentials for phase field modeling, where you put the kinetics in then for desired non-equilibrium structures, or experimental characterization as a function of process path to link to this component scale. So this, you could think of this hierarchy of scales going from atomic structure through microstructure to the component or part level as being the extension of the already existing design methodology down to finer scales. So I think the next generation of university education in MGI relevant type would acknowledge that it's not just a material selection problem, it's actually employing advanced experimental characterization in 4D, space and time type of techniques for property measurements, along with the best of computational material science to realize this bridging of information. And that's a good way to put it. Bridging of information is not so much, let's say, multi-scale modeling, it's bridging of information because the types of models we use at these different scales are completely disparate. Dynamic in the case of atomistic simulations, and thermodynamic in terms of phase field and continuum simulations. A huge condensation of numbers of degrees of freedom in terms of defect interactions, many approximations, so a huge amount of uncertainty in the forms and parameters of models. And it's inescapable. It has to be dealt with. So another underpinning element of education at university level and weaves its way through the entire MGI notion is that of treatment of uncertainty, recognition of the sources of uncertainty and the treatment of uncertainty. So verification and validation schemes that are advanced, make use of, let's say, Bayesian a hierarchical type of Markov chain model approaches and so forth. These are the elements that we have to be thinking about in terms of bridging those different scales of length and time. So this just shows that the usual way we like to think about multi-scale modeling, kind of chaining together all the way from quantum mechanics through MD and then kinetic Monte Carlo to bridge up to continuum models, reduced order descriptions, and so forth. But as we see, multi-level design of a hierarchical system has to do with moving with information flow between these levels of hierarchy, right? In the case of nickel-based superalloys, you got a blade. It may be if it's a polycrystalline blade, here's the polycrystal rendition with grains in the order of a few microns to tens of microns. These are precipitates that may range from 30 nanometers for small tertiaries up to order of micron for primaries. And then, of course, you have dislocation interaction with interfaces. It's very discrete and occurs on link scales that can be amenable to atomistic description. But the important thing is that these aren't equivalent. You know, you're not doing materials design if you're doing multi-scale modeling and vice versa. Multi-scale modeling is the servant of materials design, but they're not equivalent. This is another sort of linchpin of the notion of the Materials Genome Initiative in ICME, is that we need to get across the point in our university instruction and in our programs that multi-scale modeling is of two types, hierarchical and concurrent, and most often of hierarchical type because the uncertainty associated with passing information among scales can actually swamp the problem, and it's better to use scale-specific, high-integrity, high-confidence models rather than mixing it in with scale-bridging uncertainty, unless you have a good reason to do that, right? So a few comments about materials design in this context of uncertainty and decision-making. We view materials design largely as a decision-making enterprise. You're gathering information from the laboratory, you're gathering information from experience, from computational simulations. And so really it's a decision-making endeavor. And really the aim is to increase the fraction of critical decisions informed by modeling and simulation. Why? Because that's the way you're going to reduce the time, because it's very expensive to do that by informed through experiments, and you can't look for the classified outliers and so forth. You're not going to go to those interesting spaces. The coupling with manufacturing is quite natural. And when we talk about computationally assisted materials design, we're really talking about using computation in decision support, in a decision support role, like a lieutenant to a commander. And the systems perspective is essential here. I've attempted to show that systems perspective by taking the MGI white paper innovation infrastructure, this triad of areas that we saw earlier, and then surrounding it by the satellites, the orbit of satellites of the subfields that cross domains to connect these. So for example, you see here unit processes for manufacturing, sensors, characterization, data sciences and informatics, databases, decision-based multi-objective design, exploration, detailed design phases, knowledge system, which would be like a knowledge database in the AIM program, multi-scale models, discovery in uncertainty and uncertainty management. Those are the elements. There may be more, but those are the core elements. And let me close in a few minutes by just citing some critical technology gaps as I see them. First of all, the coupling of modeling and simulation with experiments, when you're dealing with with microstructure in particular, you're interested in the behavior of interfaces, scale effects, competing mechanisms. That's huge, right? Because you may compute something in terms of a unit process, in terms of activation energy barrier at a fine scale, but then the way they compete across scales is rather difficult to predict from unit process studies. Characterization, high throughput 4D, space and time characterization protocols, very important. Quantifying accuracy resolution requirements on measurement data sets to balance with modeling refinement and decision support uncertainty is very important. This is Julie Christodoulou, who's in attendance. This is a program that she ran, the D3D program from ONR DARPA. And this Greg Olson at Questech ran this phase, which was geared towards martensitic steels. I was involved, and a number of other individuals as you see here. But the important thing is that you can see the simulation tools over here, and you see the characterization tools over here. And it was aimed at 3D characterization, but there was a reason for that. We were trying to understand the role of these submicron precipitates and inclusions at various scales on localization of fracture processes in monotonic loading and fatigue loading, right? So we developed some understanding of what kind of information is necessary to inform localization of development of a crack tip as it grows through a ductile material. Now, in terms of computational modeling and simulation, I'll let you read this, but the important thing here, one point that I want to make is that we talk a lot in materials modeling about homogenization, that is getting effective properties of microstructures using computational homogenization or some sort of bounding homogenization approaches. But we're really interested in localization most often because we're drawn towards life-limiting failure modes in service for aerospace components. These would include fracture, fatigue, dwell fatigue, corrosion fatigue, oxidation, etc. Now, along those lines, we've been doing some work recently where we characterize microstructures in terms of endpoint correlation functions, and then develop schemes for predicting local distributions of stresses, strains, slip intensities that would drive damage in the microstructure. And that's the localization problem. The localization problem is a key, and to be able to do that efficiently enhances rapid or high throughput type of screening of properties based on microstructure. And I'll just make a few comments about a strategy we've developed within the CCMD where we compute on microstructures that are, this is just a toy microstructure here, but these microstructures for nickel-based superalloys and titanium alloys are constructed using simulated annealing to match grain and phase size and shape distributions, disorientation distributions, orientation distributions. And then we compute on a large numbers of these, involving hundreds of grains or phases each, to compute distributions of fatigue indicator parameters, which are measures of cyclic slip on crystallographic planes in the individual grains. We then look at those probability distributions, and we're interested in the tail of those distributions for the minimum life problem. And we feed that back into designing the structure through modification of the process route to enhance the minimum performance. So we can also enhance the entire probability distribution if that's the intent. But we would call this as a sort of a localization problem of extreme value type that's aimed at controlling the tail of the distribution, when often historically we're interested in just means. When you see tabulated data sets, you might see at most standard deviations, but you don't see much about the extreme values. And it turns out the extreme value distributions are of either Weibull, Frichet, or Gumbel type. And so we deal with those kinds of probability distributions. And we have schemes for basically building large numbers of statistical computational volumes, simulating them, looking for the extreme values from each. And then we plot the cumulative probability distributions according to the extreme value distributions, and then iterate in a design loop to understand whether we should control texture, control grain size, phase size distributions. Oftentimes these have to do with nearest neighbor effects. In the interest of time, let me scoot on a few slides. I was going to show here some link to actual microstructures for validation. But two final areas that I want to point to: statistical methods and uncertainty. Really, the uncertainty is a core issue, and the way we deal with that is using extended Taguchi design types of procedures, where we're looking for insensitivity to variability, and we're also looking to minimize upper and lower bounds of computed properties. As we call that type 3 robust design. There are many ways to do this, but it has to be a core foundational element of these computational structure-property relations in view of the epistemic and aleatory uncertainty that's just extensive. And we've already heard talks on the informatics and data science. I would just add that beyond data mining for screening purposes, I would say that these kinds of approaches can be used for estimating properties as well, just like we were talking about efficient methods for estimating properties. A lot of value in rapid, in high throughput methods for even approximate estimates. That has to come with the price tag of uncertainty estimates and quantification as well. That's essential to understand the value of information that's involved. Now, a closing comment here about workforce issues. I think we've talked a bit about this, but it is sort of a cart before the horse thing, because the fact is we're not really teaching students in universities, and there aren't enough people in industries that kind of yet populate the landscape to pull all this off. So a major initiative, I think, of MGI has to be workforce development. And we've just got to have a broader systems perspective that we impart. We saw in the previous talks, I mean, the incredible richness of the stochasticity, the data mining, the informatics, the first principles combinatorial approaches that really haven't found their way into our curriculum yet, right? Into our curriculum in universities. That needs to be there, but the capabilities need to be there in terms of faculty as well to do that. So we need good instructional materials. We need some foundational materials at this point. Just developing tools and methods won't really add enough. I mean, just because we can do it through one outstanding PhD doesn't mean that gets transferred. We have to create systematic ways for transferring this. So that means new curricula. It means interdisciplinary collaborative activities across universities. I can't think of a single university that can pull together all those orbiting satellite subfields around the MGI innovation infrastructure that I showed earlier by themselves, right? So from our perspective, I think we ask the question, where are the technology gaps, the primary obstacles? And it can differ from the usual questions academicians ask about things like multi-scale modeling. And how can we, drive workforce development with educational programs? Probably the most important thing that universities can do, aside from all the clever things that we do with modeling and simulation and design, probably the most important thing we can do is create the future workforce by providing a proper educational environment.
Thank you, David. We have time for a few questions.
Yeah.
I'm glad you pointed out the education part, because it's one we struggle with and argue with at MIT and never come up with a solution either. So part of the problem lies in that when you talk about systems level thinking, that you often have to get specific. And so analyzing what goes into a jet turbine, it's not the same system level thing you need to know as if you're going to the same HVAC, for example. And we have found it very hard to get people to think at the more abstract level is, it's actually the method of system level thinking. Now the business school people do this. They have the same problem. They have to teach people how to analyze, and they do case studies, and maybe it's as simple as that. Maybe we end up doing a bunch of case studies. And the other struggle you find is that, well, some people say, well, we should do all system level thinking, but then if you ask them, is that okay if the students don't know their thermal anymore? So at some point you have to trade something up. We already have curricula that are very full, and getting people to trade up stuff makes it a lot harder.
I think systems level thinking by itself is not the way to go, because the only reason we're making progress in this field at all is through physics-based modeling. That's the value added to it. But I do think that, there's a lot of value in curriculum development, basic textbook. So for example, we wrote a book published by Olsen in 2009 on this robust design idea. What are the systems level issues common to designing a wide variety of things, and how would they be modified to consider all the vagaries of designing materials, right? And I listened to, we were talking on searching data mining and informatics, appreciate it. I think, well, I'd love to see a textbook in that area, right? A really nice, solid, foundational reference that you could use for senior level undergraduates and introductory graduate students. Very easy. It says, here are the existing methods. They'll change in 10 years, but by God, this is what we're going now. I think this is the kind of level of information we need to build senior level elective and graduate programs on to really drive the